Okay, so we're finally in calculus now. Limits. Limits is the first real calculus unit, and it's theory, algebra-like. So you can like it. Everybody have their calculator to that? Okay, I'm going to attempt to use the blue one up here and see what happens. Is it better with lights off? Finding limits numerically and graphically. I mentioned before, but you may not remember, that for the AP exam, you look at things, you do table, that's the numerically part, graphically, algebraically, and then you may have to write a sentence or so every so often. So today we're going to look at tables and graphs. Tomorrow we'll look at the algebra side of limits. Okay, so we first have this function, f of x. First question is, where is it undefined? X is 1. Right? The denom will be 0 then. Okay, so let's complete the following table. You're going to need to take your calculator and in y equals put this function. Whole top has to be in parentheses and whole bottom as well. So in parentheses x cubed minus 1. Way slower than yours. Maybe that's good. I don't know. Okay. From there, I'm going to second put out, and then you can do vars y bars. You'll have to do vars y bars because really those aren't going at a regular interval for your x's, right? So from here, vars, y bars, function, y1. You don't have to close your parentheses if you don't want to. Like so. And that'll be your first entry in the table. Okay, so let me give you a couple minutes to see how that goes. And I'll fill in with you as we go here. And although I know we did talk about going 3 decimal places out, for now we might have to go a few more. Yeah. Put a couple up there, make sure you're on the right track. Does that look like what you're getting? How about the 1? Error. We already kind of talked about why that is, right? That's where the thing's undefined. So what we're doing is looking at a place where x is 1. This is kind of the middle of our table right there. Okay. And what we're doing is approaching an x value of 1 from the left. Here's from the left. And also from the right. So what a limit will be is that y value that we're getting really, really, really close to as we get closer and closer to an x value of 1. It doesn't really matter what's happening at 1, only when you get really, really close. So what y value would you think you'd be approaching from the left and the right? 3. Would you agree, everybody? Being really, really close to 3? So 3 is actually your limit in this case, and you can tell by looking in the table. Let me scroll up just a little bit. Another way of looking at the same situation. This is the graph, or piece of the graph for that table. It's a parabola with a hole in it. The hole happens to be at the point 1,3. Reason being that 1 makes the thing undefined. So as I get really, really close to 1, again from the left, or down here from the right, I'm approaching a y value of 3. So you get the same idea from looking at the graph as you do from the table. Here's the way it's written. LIM for limit. Okay, it's the limit as x approaches, you write a little arrow, x is approaching 1 of f of x equals, in our case, 3. Okay. Let me say it one more time. The limit as x approaches 1, getting closer and closer to 1, of f of x equals 3. The limit's always the y value, which you're getting closer and closer to. Okay, so far? So let me label this graph a little bit. This will be L, capital L standing for limit. And this 1 down here will forever now be known as little c. And the x value that you're approaching is little c. So down below that it says this leads to an informal definition of limit. If f of x becomes arbitrarily close to a single number L, closer and closer to 3, as you approach your c value, which is 1, that y value, in our case 3, is called the limit. And if I wanted to write the limit just kind of generally without actual numbers in here, I'd write the limit as x approaches c of f of x is L. Can I go on to the next page? Okay. Let's look at number 2. It says, find the limit as x approaches 0 of sine x over x. Right now, all we have is the graph of this, or we can look at a table for this. I want to do both things. So let's go to the calculator. Make sure you're in radian mode. You probably are. That's your default, and we don't really use the degrees at all. So let's go ahead and plug this in. Sine x, and you don't have to put the entire thing in parentheses. I experimented earlier. Divided by x. That. Okay? And second put out of there. We can just look at the graph. Let's just do a zoom 6. We'll adjust if we need to. Okay, and we could zoom in on this thing, certainly. Let me trace. Can everybody get this graph? Okay. Notice what's going on here is I hit trace. I'm right at what would be the y-intercept, but there's no y value there. Why do you think that is? Yeah, it's undefined. You can't have a 0 in the bottom. There's an X in the bottom, right? You can't have a 0 in the bottom. If I move left or right, okay, let me kind of go back towards 0. Notice this y value as I go to the right. Looks like it's getting closer and closer to 1. And I could do the same thing over here on the left-hand side. If I come in from the right, I'm getting closer and closer to 1 as well. Good with that? Okay. Now let's look at it from a table or numerical perspective. Let's do second table set. I'm going to start my table at whatever I'm approaching, whatever x value I'm approaching. In this case, I'm approaching x equals 0. So I'm going to start at 0, so change it to 0 if yours doesn't say 0. And then I want to be really, really close to that, because I want to see what's going on when I'm really, really close to 0. Okay, I can't get right on it because I know that's error. Right, there's no point right there. So I don't know, you make up a number, 0.001, let's say, 0.001. Just something really, really close. Now let's go to the second table. Okay, and let me back up a little bit so I can see both sides of 0. Okay, here I see coming in from the left and also coming in from the right. Notice my y values. Right, 1, 1, 1, 1, 1, 1, 1. So by looking at the graph and by looking at the table, we can tell that this limit is 1. Okay? So if you want to, if you think it'll help you as far as doing your homework tonight, do you want to go ahead and write down some of this table here? Would that help? Okay, let's do that. Just as a reminder of what you're supposed to do tonight. I'll do this. Table start, in this case, x equals 0, and then delta table, 0.001. So just to remind you. And I'm just going to copy what we had on our table. We're going to do something similar with the next one. The same type of thing. We can look at the graph. We'll do the same thing as far as starting at 0 because this one's approaching 0 as well. So let's go back to the calculator. Whole top of this now is going to have to be in parentheses. I don't know what will happen on Zoom 6. Let's just look and see. Oh, that's okay. We could always zoom in. It doesn't really matter. Hit trace. Notice that same thing's happening, right? And you could again move just to the left of it and kind of approach from the left, or just to the right of it. What does it appear that the y value is approaching when x is approaching 0? 0. Does everybody agree with that? Okay, let's do the table way. Let's do second table. I'm going to start at 0 again. And 0.001 again. And once I get my table, I'll back up a little bit. Oh, what the? Yikes. Yikes, what are these things over here? Yeah, these are some scientific notations, right? These are some scientific notations. So keep that up on your calculator. I'm going to go back here and write that down for you. Actually, let me get closer to the left. we started with 0.003. Okay. What the calculator said was, I think that was just a regular decimal, right? Negative 0.15, right? Okay. This next one was the scientific notation one, right? 0.02. This one said negative 1 times 10 to the negative 3. That's what that E means, right? Oh, it's still there. Cool. Thanks. Okay, the little E, right, just means times 10 to the negative 3. Okay, so think of your decimal point being right there, and you've got to take it 3 places left. It's 1 place to get around the 1, right? And then 2 more to the left will give you negative 0.001. Okay, then negative 0.001. This one says negative 5 times 10 to the negative 4. So this one of your places to get around 5, so negative 0.0005. This one's the error. And then these guys are the positive counterparts to these other ones, right? So going from the top down, right, that's from the left. These numbers getting closer, closer, closer to 0, right? And here, going up from the bottom, that's heading in from the right, numbers getting closer, closer, closer to 0. Any questions on 2 or 3? No? Okay. Number 4. Let's look at another picture. This one's piecewise. Find the limit of f of x as x approaches 2, where f is defined as 1 when x isn't 2, and 2 when it is. Okay, so there's a little dot right there if you didn't notice. A little dot. So what you want to do is you want to approach 2. We're doing the limit as x approaches 2. Let me write that. The limit as x approaches 2. Now remember, you have to approach it from the left and the right. So come in from the left and the right. I don't care what's happening at 2, only when you get really, really close. So what y value is it approaching when you get really close to an x value of 2? 1. That's right where the open circle is. Does everybody agree? Okay. X equals 1. So that's our limit. By the way, you'll be asked this some other time. If you were not asked the limit, if instead you were asked, what's f of 2? That's old school, that's last year, that's A2 trig. That's asking you now, what's the actual function value when x is 2? That's the dot. So what would you say here? It's this dot. 0. Right? So when x is 2, y is 0. Okay? Okay.
I don't know whether you're looking at the dot or not.
Whether you're looking at the dot or not, when you're doing a limit, you're going to look at this number. You only want to know the y value when you get really close to that number. It doesn't matter what's actually happening at the number for limits. Okay, we're going to do some more anyhow. Look at this one. Okay, limit as x approaches negative 1. Okay, over here. So what y value are we approaching as you approach negative 1, just tracing this curve, right? As you approach from the left and from the right. Looks like it's approaching a y value of 3. Okay. This one's 3. Three halves. Let's approach 3 halves. That's 1 1/2. 3 1.2? Maybe, ish? Estimate? 1.2, did you go for that? Okay. How about 1? Yeah, this is an error. It's exactly right. If I approach from the left, I'm way up here. If I approach from the right, I'm way down there. It's not approaching the same y value from the left and the right. So this particular limit, the one in C, does not exist. And we have a neat little way of writing that. We write DNE. In other words, that limit does not exist.
So just for error.
Okay, last one on this one, 2. What would you say for 2? Limit as x approaches 2. Sorry? 2.8, I'll go for that. 3. Say 2.8. We're estimating, that's fine. Questions so far? Okay. Here's some more limits that fail to exist, or that are DNE. Number 6, behavior that differs from the right and left. That's exactly what we just saw. And one where Emily said error. So if we look here at the limit of f of x as x approaches 2, look what's happening. As I approach 2 from the left, my y value is different than if I approach 2 from the right. Everybody agree? So I don't even care what the y values are, to be quite honest with you. This is DNE, I know that. Unbounded behavior. The limit as x approaches 0 of this. These guys are actually asymptotes. You won't necessarily always see the arrows here, but they're there. You have asymptotes here at the x-axis, right? Those curves are reaching out toward the x-axis but never going to touch it. Same thing up here. These guys are reaching toward the y-axis but never going to touch it. I like to call this one a volcano for obvious reasons. So you might say, well, as you approach 0, they're going toward the same thing, right? They're going up, 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 up to positive infinity. Okay. So we could say positive infinity. And for some test questions, you'll have to answer it like that. But do know that infinity's not really a number, right? It doesn't really exist. So another answer to this could be does not exist. So how would you know which one to write down? Well, if you had a question like this, it would probably be a multiple choice, and there wouldn't be both those answers there. So it does not exist, but sometimes you kind of have to tell in which direction it does not exist. Okay, what the heck is this little guy? This gray little rectangle means too many wiggles, crazy oscillations, as fast as you can go. So this oscillating behavior, I like to call it too many wiggles. It's just crazy oscillation of this graph. In other words, when you get in there next to 0, the graph's just going up and down so fast it's not approaching any one number. So this one also, DNE. So if ever you see a shaded thing like that, that's what it means, crazy wiggling. Not so bad so far, right? It's doable. Some pictures, I like it. Okay. I'm going to give you a brief preview of the formal limit definition. The formal definition involves a couple of Greek letters known as epsilon and delta. I don't know if it's D and E in the Greek alphabet. You are not going to be tested on the AP on epsilon and delta. It's one of the couple things we'll do this year that I'll show you that isn't on the AP. The reason I show you this is that any calculus class you're going to be in college, if you retake Calc 1 or you're into Calc 2, you're going to see epsilon and delta. So so at least you'll have seen it. We won't do very much with it, but at least you go, oh yeah, I remember epsilon and delta. Okay, so basically, we have that same situation we have for a different graph. We have this little c value. This is the x value that we're approaching, that little c value down there. This is your limit over here. And epsilons are in here. They're always the distances from your limit. And they're normally the same number. And you'll be told how far away from that limit they want you to be. So basically what the definition says, if we're corralling that limit on either side by some distance epsilon, you can use your calculator, you can use a graph, you can just kind of go over and down just like they are on this particular graph. And then you'll be some distance away on either side of that c value. Okay? The distances down here are known as delta, Greek letter delta. Okay? Delta, they may not always be the same. For the ones we're going to deal with, they'll be the same or they'll be really, really close to each other. If you get two that are a little bit different, just pick the larger one. We'll deal with that in a little bit. So that's kind of the picture of the epsilon delta situation. Let's get into a problem and then we'll kind of end the problem with epsilon and delta. Come on. Okay, so we got a new problem. It says graph this on the calculator and sketch it there. Again, remember parentheses around whole top and whole bottom. There's a line, right? You can trace it. Trace along it. Not a problem. There is going to be a problem someplace, though. Where do you think the problem's going to arise? At 5. So now that we're tracing, let's just hit 5 and enter. No y value there. So what that's telling you is there's a little hole in the graph. Your calculator won't show you on the picture the little hole. Okay? You could only show the little hole, for example, by tracing like this, or by looking at your table. Okay, so let me go back and draw this. Let me sketch it here. I don't know how good I'll do sketching on the smartboard, but we'll try. Okay. I know the hole's out here at 5. Okay, and I also know back to my graph for 1 second. I'm tracing. Go to 5. Let me kind of look at some values right around the x value of 5. Look at these y values here. What are they really close to when x is close to 5? 4, right? So my hole here, hole is going to be a 5, 4. Okay, and let's go ahead and complete the table. This time you could do a table set because the x values are at regular intervals, if you want to. You could do second table set. Start this at 4.6 and count by what? 0.1. Okay, and And there's your table. Can everybody get that table to come up? Okay, so go ahead and copy it into your table here. Get used to that. And then so again, you're looking at this from the point of view of a table, approaching 5 from the left and approaching 5 from the right. Right, the limit here is going to be limit as x approaches 5, I think this was called that, is what? 4. Question, Valerie?
For these, do we still have to answer like decimal points?
For your tables?
Or like the limit
Okay. What's happening at 5? We kind of talked about that already. There's a hole in the graph. Why is there a hole in the graph at x equals 5? Yeah. X equals 5 makes f of x undefined. Okay, and lastly, what is this graphical feature called? I don't know if I've ever told you this before. It's called a removable discontinuity. Discontinuity. And yes, you will have to know that. So we kind of looked at the table. We looked at the graph. We're going to carry on with this very same problem. Here it is again. Let me write the problem up top. I didn't rewrite it on this page, just so we got it here. Okay. It says try to find f of 5 by substitution. Let's do that. And I'm not going to do bars by bars. I want to actually show this because I want you to see what's happening. So I'm going to do 0.4 squared minus 10 all over 5 minus 5. Okay. Go ahead and in your calculator, type in the numerator. Type in 0.4 times 5 squared minus 10. What do you get? What's that? 0. Yeah, well, and obviously in the bottom you get 0, right? Eee. Okay, this is something special. This has a name. This is called the indeterminate form. Indeterminate form. It's not the only one. one. There's actually several indeterminate forms. This is just one. This particular one, when you get it, and you'll get it a lot, this basically says to you, do more work. Do some algebra. Okay, bless you. So anytime you get this 0 over 0 indeterminate form, you're going to need to do more work. So right now, we're going to need to do more work. I want to try to make that big. I don't think I need the calculator anymore. Okay. So now I'll factor. Take this thing and factor it. On the top, right, I'm going to take that 0.4 out of there. The 0.4 out of there. If I take the 0.4 out, I'm going to have x squared minus, I have to figure out what can I multiply by 0.4 to get 10. All right, so try, what can I multiply by 0.4 to get 10? So divide, right? Do a little division there. Anyone? 25. Okay. Now I'm good. Now I can just keep going, right? Factor some more. This is the special x plus 5, x minus 5. Okay. And I'm going to cancel that. And that's going to take care of my 0 over 0. That's the reason I was getting it. So now that I'm this far, I can go ahead and substitute back in. So I'll do 0.4. Okay. Now I'll try putting that 5 back in there. So I'll have 0.4 times 10, or just 4. And that's exactly, if you go back a page, what you told me the limit was. So we looked at the limit via a table. We looked at the limit via a graph. And now we just algebraically determined the limit in all of those cases to be 4. Question?
Can you do that with quiz without calculator?
No.
Can I go I'm not having a quiz?
What?
Can I go not having a quiz on this stuff?
No. So here's kind of a summary of what we just did. The number 4, which f of x is close to and x is close to 5, is the limit of f of x as x approaches 5. You can make f of x as close as you like to 4. Kind of like the trace key. Just by keeping x close enough to 5. So here we go, back to epsilon and delta. And this will kind of finish out the day for us. Same problem still. New table. Okay? Go in with your bars, Y bars, and fill in that table. Let me give you a couple minutes for that. says let's keep f of x within 0.01 unit of 4. Let's keep f of x within 0.01 unit of 4. It's a little bit easier to think about this if you look at the picture here. Let's see if we can make this a little bit bigger. Okay, looking at this picture, you can see you're adding 0.01 to 4 and subtracting it from 4. So those are kind of your boundaries on the y's. That distance, that 0.01, is called epsilon. Okay, so I'm going to make like little e's in here. That little distance there, that's your epsilon. On the table, here's another way to look at it. The distance from that y value of 5, or from the hole there, to 3.99, this distance here is 0.01, which is epsilon. Same thing down here. Okay. Epsilon will be something that you're given. You have to determine then if your epsilon, or 0.01 in this case, from 4 on the y-axis, how far are you then from your little c value down here? In our case, 5 on the x-axis. And this is kind of showing you the over and down on the picture to correspond with your table. Notice those are exactly the values you come out with in the table if you go 0.01 up and down from your y value of 4. Okay. These distances in here are your deltas. So delta in our case will be how far away from 5 are we? True? That's how far away from 5 we are. Okay, and we can look at that same thing over here. This is 0.025 or delta. Okay, so far? We're almost done. Almost done. Can I turn the page? You can also use algebra to find out exactly how close to keep x to 5. Let's stick with our epsilon value of 0.01. Let me show you a little algebra trick to come up with the delta. We know, if you look back at the prior page, that the boundaries from that y value of 5, sorry, of 4, were 3.99 and 4.01. Let me go back. Here we go. Here they are. So we're taking those now. I'm going to do a little bit of algebra with them. You could. It doesn't really matter. Okay, now I'm going to put f of x in there. F of x was, and I'm going to use the simplified version. Here was what we had when we simplified it. After we get done factoring and canceling. So let help you before I go any farther. Write this. Simplified version. And then let me go ahead and multiply that out. So 0.4x, I'm distributing this, plus 0.4 times 5 is 2. Okay. And this was an Algebra 2 trig thing that we did. Now we want to get x all by itself in the center. Okay, so we're going to have to subtract 2. That's the first thing to do. We've got to do it from all three pieces, though. So if I take 3.99 and subtract 2, I get 1.99. Here I'll subtract 2, and then 2 will be gone. And then lastly, subtract 2 here, I'll get 2.01. Okay, now I'll have to divide everything by 0.4. So if I divide 1.99 by 0.4, I should have 4.975. And for some of these, you might have to go out a bunch of places. And over here with the 2.01, that'll become 5.025. So that's not your answer. Your answer is, how far are those two numbers, 4.95 and 5.025, from your C value, which is 5. So how far are they from 5? Yeah, they are 0.025. And again, this isn't something that's going to show up on the AP, but it is something that if you go to calculus in college, you'll probably run into. And it's really not too bad. Any questions on that? Okay, we'll try a couple more here. These guys will just be written a little bit differently. Here we have a line for x minus 7. It says the limit as x approaches 3 is 5. Okay, so here's our C value. C. Here's our limit. It says epsilon is 0.1. This is shown to you in the picture. This is my epsilon. So add 0.1 and subtract 0.1 from 5 to get those two values. And it says determine delta. And that's a lot of inequality and absolute value stuff looks confusing. Okay? Basically, it's back to A2 trig again. This absolute value means distance. This is the distance between, can I do that with between? Distance between f of x and 5, in our case, is less than 0.01. Okay, so in other words, these little distances it's talking about, the distance between your y value and 5. So they're just telling you how big epsilon is in a fancy way. Okay, and then they want to know the distance then from x to 3. So they want to know the deltas. It's just another way of saying some of the deltas. So we're going to do just what we did before. You're going to take these two y values here. So take 4.99, put f of x in the middle, and 5.01, and go from there. I'll put f of x in this time. F of x is 4x minus 7. That's as simplified as that can possibly be, so I'm good there. And the first thing I'm going to do now would be to add 7. So 7 and 4 is 11. This will be 11.99. This will be 4x. And this will be 12.01. And now it's calculator time. So dividing by 4, this should be 2.9975 and 3.0025. Remember, you're looking for these little distances in here. So those aren't your answers. You need to tell me how far away those numbers are from 3. 0.0025. That's your delta. Any questions? Let's try this one more time. Here we have a little piece of a parabola. We have the limit as x approaches 2 is 4. We have an epsilon of 0.001. We need to find the deltas. X is pretty simple this time. Looking at the graph, I also don't have any worries about the negative root. Right? I can use the principal root, right? When you do the square root, you get 2 answers, right? I don't need to worry about that. I'm definitely over here on the positive side. So I can go ahead and take the square root across the board here. This will give me 1.99975 and 2.00025. Delta is 0.00025. Any questions at all? I think I would like to graph the piecewise function with you on the next page if I could. I don't have it in here though, so I'll put it in here. Take just a sec. If you remember how to do piecewise, you can actually start graphing it. If you don't, you may want to wait a sec. This is actually kind of a gentle one. There we go. I think we'll still zoom it up a little for you. Okay. So this is a 3-parter, has 3 branches. The first branch is a line. What's the middle branch going to be? Dot. Yep. And the last one? Parabola. Yes. So you want to kind of start looking here. So looking at the top branch, looking at an x value of 2. If I were to plug into the top branch an x value of 2, I would get 3. Meaning the point 23 is got to be graphed. Although, this is just a less than sign and not less than or equal to, so it's actually going to be an open circle at 2, 3. say as to why we're doing 2, 3? Okay. So I'm going to see this line for open circle and then some values less than the value of 2. So let's try 1. If I plugged a 1 in to the top branch, I would get, okay, 1, 2 would be a dot. How about if I plugged in 0? 0, 1 would be a dot, and so on. I could draw this one. Bear with me, I'm going to freehand it. Not too bad. Okay. And then Mallory said that the middle branch is a dot. Where's the dot? 2, 1, right? 2, 1, there's a dot. And now the parabola. If you'd rather, go ahead and plug it into your calculator and do bars, y bars. That may be the easiest thing. Let me give you a second to put that into your y1. It'll be pretty fast, not even a fraction. Okay, and then start by doing bars, y bars for a value of 2. So when x is 2, y is 3. Oh, look, we have that. It's the open circle. So we have an open circle on top of an open circle. Okay, now let's go to the right because these are for x greater than 2. So plug in a value of 3 now. That'll give you 2 to the point 32. Okay, and 4. 4, 3. Or you could look at a table if you wanted. 5. 6. That's probably good. So here's my parabola, rough sketch. Anybody have a question on how to get it graphed? Okay. Because you'll have just one of these then on your homework tonight. Can I scroll it up a little bit? I want it to be off, but... Okay. Because the equation y equals x plus 1 is used only for x less than 2, and the parabola only for x greater than 2, there's a discontinuity at the end of each branch. Are these two discontinuities at the same point? Yeah, they meet at the open circle, right? The discontinuities are at the same point, yes. Yes. Okay. Does f of x have a limit as x approaches 2? Does f of x have a limit as x approaches 2? Yeah, remember, it doesn't matter what's happening at 2. Only when you get really, really close. So what is the limit as x approaches 2? Everybody reads 3? It's the y value you're getting close to. So does it have a limit? Yes, it does. Okay, the limit as x approaches 2 of f of x is 3.
We have to write that on the calculator.
Every single time. Okay. Is f of 2 equal to the limit? Is f of 2 equal to the limit? Greg's saying no. Explain, explain. What is f of 2?
Undefined.
There's a point at f of 2. Nope, it's undefined there. Where's the dot? Where's the dot? 1, right? F of 2 is 1, isn't it? Would you agree that's what a closed circle is? Okay, so that's not the limit. F of 2 is the closed circle. That's no calculus there. That's just asking you, at an x value of 2, what's the y value? Okay, f of 2 is 1. So this answer to this is no. F of 2 is 1, and that does not equal the limit as x approaches 2 of the function. As you know, that's 3. And very last question. The graph of f is discontinuous at x equals 2. In other words, to trace it, you'd have to pick your pencil up and hop over that little open circle. What number would f of 2 have to be in order to make the thing continuous? Yeah, it would have to be 3. X would have to be 3. In other words, you'd have to fill in that circle. You'd have to fill in that closed circle. Sorry, x and y. Let's try again. Let's say when x is 2, y would have to be 3. That's better. Y would have to be 3, or f of x would have to be 3. Another way to say this would be f of 2 would have to be 3. You have to fill in that circle. Okay. Let me write homework down for you, and I want to kind of go through it real quick with you and have you scribble out some directions. I don't want you to have to do all the explaining and writing that this is asking you to do. I'll be unhappy about that. So, the only one that needs graph paper is just 23. It's none of the other ones in there. Okay. Pull out your homework paper as soon as you have these written, because I want to give you some hints and whatnot. Okay, everybody looking at page 1 on the homework packet. Page 1 on the homework packet. Oh, no, I don't know about you. Okay, if you look at the directions there for in exercises 1 through 8, complete the table and use the result to estimate the limit. Okay, you can cross out the second sentence. You can cross out use a graphing utility to graph the function to confirm your result. You don't have to do that. Cross that second sentence right out. Sorry, you guys are guinea pigs for my new packets. Okay, and then you can turn to the next page, to page 2. Upper left is page 2, where it says in exercise 9 through 18, use the graph. You can cross out, if the limit does not exist, explain why. We're going to do that verbally, and you're not going to have to write it, so you can cross that out. If the limit does not exist, explain why. Now if we skip over to 19 and 20, you can cross out again, if not, explain why. We're going to do that together. have if you turn the page. Just an FYI. Number 25 is one that you'll have to do. Just make a little sketch. You don't have to do graph paper or anything like that. Just a little sketch, and there's more than one correct answer. We'll just give that a whirl, see how you do. Now I'm going to skip with you all the way to 33. I want to give you a hint on 33, actually. Hint on this one. This is the limit as x approaches 2 of 3x plus 2. Okay? And the basis of this question is the epsilon delta thing. They want you to find delta. But before you can do that with the inequalities to find delta, you have to know what the limit is. So here you'll have to either use a table or look at a graph and figure out what this is first. So without this, you can't do this question. So find the limit first. It does say that, but it's not obvious necessarily. Because that's the number you're going to have to go to the left and right of to start. And if you don't know what that number is, you won't be able to do that. Oh, yeah. Page 4. See that paragraph on the left that says writing and exercises 49 to 52? You can cross out everything except the first sentence. You don't have to do any of that, just the first sentence. Use a graphing utility to graph the function and estimate the limit. And you can even write there table. I would probably use a table instead of a graph. Or you can look at graph and table. I'm kind of interested that you can make the table for 49 and 51. One more, I'll give you a little hint on 41 also, on page 6, very last one. Very, very last one. Just because the question's worded kind of weirdly. Everybody look at 41, page 6. It says, use the graph to determine the limit, that's no big deal. Write a simpler function that agrees with the given function at all but one point. How do you take 41 and write a simpler function? What are they really asking you to do? Yeah, factor or cancel. That's all you have to do there. That's what they mean by write a simpler function. Okay. Many of these will go very quickly. Just look at a picture and say the limit.